The observable universe refers to the portion of the universe that we can observe and study using telescopes and other instruments. However, this capability is limited because light, the main source of information about the universe, can only travel at a finite speed. As a result, we can only observe objects or events that are at a certain distance from us. Objects or events that occurred long ago in the past cannot be seen directly. The observable universe refers to the enormous region of space that humanity can detect and examine using advanced instruments like telescopes and other scientific tools. However, this ability to observe is inherently limited by the speed of light, our primary carrier of information across the cosmos. Because light travels at a finite speed, we are only capable of observing celestial objects and phenomena whose light has had enough time to reach Earth since the beginning of the universe. This imposes a cosmic horizon beyond which we cannot currently see, not because those regions do not exist, but simply because their light hasn't yet arrived. Despite the universe being approximately 13.8 billion years old, the observable universe spans an estimated 93 billion light-years in diameter. This seemingly contradictory scale is explained by the ongoing expansion of space itself since the Big Bang. As the universe has expanded, galaxies have drifted farther apart, and the light emitted in the early universe has taken a longer, more stretched path through the inflating fabric of space before reaching our instruments. Thus, what we can observe is vast, but it still only represents a fraction of the total universe, leaving an immense unobservable region beyond our current technological reach. Thanks to cutting-edge space telescopes like NASA's James Webb Space Telescope, JWST, astronomers are continually pushing the boundaries of what we can observe, peeling back layers of cosmic history. JWST, following in the legacy of the Hubble Space Telescope, was specifically designed to look deeper into the universe than ever before, focusing particularly on the infrared spectrum. Infrared light is crucial for viewing extremely distant galaxies whose light has been redshifted due to the universe's expansion, a phenomenon where a wavelength of light stretches as space itself stretches. Using this technology, JWST has captured images of galaxies that formed just a few 100 million years after the Big Bang, offering unprecedented insight into the early universe. These discoveries have revealed active star formation taking place in these early galaxies, helping scientists understand the processes that shaped the young cosmos and built the complex structures we observe today. Such revelations do more than merely inform scientific models. They provoke profound philosophical questions about our existence and the possibility of life beyond Earth. For generations, humans have looked skyward wondering whether we are alone in this immense universe. The growing list of exoplanets, planets orbiting stars outside our solar system, has transformed this wonder into a legitimate scientific pursuit, using techniques like the transit method, which detects slight dips in a star's brightness as a planet passes in front of it, and the radial velocity method, which measures the gravitational wobble induced by a planet on its host star. Astronomers have discovered thousands of such worlds. Among them are planets with strikingly Earth-like characteristics, right down to potential atmospheric compositions that might support life. A particularly thrilling case involves the exoplanet WASP 96b. When JWST analyzed its atmosphere, it detected water vapor, haze, and clouds, indicating more complex and potentially life-sustaining environments than previously anticipated on such planets. While no direct evidence of extraterrestrial life has yet been found, these findings make it increasingly difficult to dismiss the possibility that life could exist elsewhere in the universe. But what lies beyond the borders of what we can observe? The limits of our current observational range raise tantalizing questions. Theory suggests that the entire universe could be at least 10 to the power of 23 times larger than the observable part, owing to the rapid inflationary period that occurred shortly after the Big Bang. This concept of cosmic inflation proposes that space expanded exponentially in a fraction of a second, making it plausible that regions far beyond our observational limits exist, perhaps with entirely different structures, laws, or forms of matter. If faster-than-light travel or wormholes, hypothetical tunnels through spacetime, were ever proven viable, we might one day glimpse these distant realms. However, These ideas remain speculative and largely within the domain of science fiction for now, as they require technologies and understandings of physics that are far beyond our current capabilities. Despite the vastness of the unobservable universe, cosmologists continue developing theories to better understand the cosmos. Some of these ideas, while grounded in observation, tread into speculative territory. One such concept is the multiverse, the idea that our universe is just one of many. This theory finds roots in quantum mechanics and inflationary cosmology. The many worlds interpretation of quantum physics suggests that every quantum decision spawns a branching reality where all possible outcomes play out in parallel universes. Similarly, the inflationary model allows for regions of space that inflate differently, creating bubble universes with unique properties and physical laws. While these ideas are intellectually stimulating, they lack direct empirical evidence and remain the subject of philosophical and scientific debate. Some physicists find the multiverse an elegant way to explain fine-tuning in a universe's constants, while others caution that without observable confirmation, it is no more scientifically valid than any untestable hypothesis. Another enigmatic idea in cosmology is the notion of dark flow. First proposed in 2008, dark flow describes the observed motion of galaxy clusters that seem to be moving in a consistent direction faster than what can be accounted for by known gravitational influences. This suggests the presence of a gravitational force or structure beyond the observable universe, potentially hinting at even larger cosmic formations pulling on these clusters. While intriguing, dark flow is controversial. Some studies support the existence of such directional movement, while others argue that it could be due to observational errors, statistical noise, or incomplete data. Regardless, if validated, dark flow could imply a large-scale structure or gravitational force exerting influence from beyond the cosmic horizon, a finding that would challenge the cosmological principle that the universe is homogeneous and isotropic on large scales. The progress made in observing and understanding the universe owes much to the pioneering work of telescopes like Hubble and JWST. Hubble's ultra-deep field image provided one of the earliest looks into the distant universe by capturing thousands of galaxies in a tiny region of sky, demonstrating just how rich and crowded the cosmos is even in seemingly empty areas. JWST has taken this to the next level by extending our view further back in time, revealing galaxies that existed just a few 100 million years after the universe's birth. These observations help scientists reconstruct the timeline of galaxy and star formation, offering clues about how matter first gathered into the structures we now see. Some of the most surprising findings include the detection of massive, well-formed galaxies existing far earlier than expected, an observation that challenges current models of how long it takes for galaxies to mature and may require a revision of our understanding of cosmic evolution. Such discoveries also tie into the mystery of dark matter and dark energy, two unseen yet profoundly influential components of the cosmos. Though invisible to telescopes, dark matter is believed to make up about 27% of the universe's total mass energy content. It acts as the gravitational glue that holds galaxies together and affects the way galaxies rotate and cluster. Dark energy, which constitutes nearly 68% of the universe, is even more mysterious. It is thought to be responsible for the accelerating expansion of the universe, a revelation that came as a shock to scientists in the late 1990s, who had previously assumed that gravity would slow the expansion over time. The realization that approximately 95% of the universe is composed of things we cannot see or directly detect emphasizes how little we truly understand and underscores the need for continued exploration. As our instruments become more sophisticated, we will continue to refine our knowledge and perhaps one day gain direct evidence of phenomena like dark flow or parallel universes. Until then, these concepts serve as powerful reminders of the universe's vastness and complexity. They reflect the limits of our current scientific understanding, but also the boundless potential of human curiosity. With every new image from the James Webb Space Telescope, every newly discovered exoplanet, and each theory that dares to question our assumptions, we inch closer to grasping the full story of the cosmos. We are explorers of time as much as space, looking back billions of years when we peer deep into the sky. The most distant galaxies observed today shine not as they are now, but as they were long ago, their ancient light just now arriving at our detectors after a journey across a constantly expanding universe. These celestial fossils offer a window into cosmic infancy, into the birth and growth of stars and galaxies, and into the very fabric of space-time. In the end, the observable universe is not just a map of where things are, but a timeline of how everything began. It is filled with wonders, from infant galaxies to strange unseen forces shaping the cosmos. And it continues to challenge our most fundamental beliefs about existence. While we may never fully understand what lies beyond our observational reach, the pursuit itself enriches our understanding of the universe and our place within it. Science does not demand all the answers at once. It demands that we keep asking questions. As long as humanity dares to look up, to wonder, and to explore, the story of the universe will keep unfolding, one discovery, one observation, one insight at a time. Even as scientists debate the boundaries of observable reality, the implications of these theories stretch deep into both philosophical inquiry and future technological aspiration. The very suggestion that our known universe is one of many triggers questions not only about the structure of existence, but about our own uniqueness, or lack thereof. Could there be versions of ourselves, other Earths, or completely foreign configurations of matter, time, and consciousness in these theoretical sibling universes? It's a question that challenges both empirical science and the imagination. These ideas, though difficult to prove, are not dismissed outright. Instead, they serve as a springboard for new models and hypotheses in cosmology. With increasing computational power and advancements in quantum theory and particle physics, some hope that signs of other universes might one day be inferred through indirect evidence, perhaps through subtle anomalies in the cosmic microwave background radiation or unexplained features in the structure of space-time itself. As we contemplate such grand possibilities, we must remember that our most basic understanding of the universe is still evolving. Even fundamental questions like the exact geometry of space, the fate of the universe, or the true nature of time are far from settled. Theories about the shape of the universe, whether it's open, flat, or closed, continue to evolve as more precise measurements are made. Observations suggest the universe is very close to geometrically flat. But tiny deviations could mean it curves in on itself on enormous scales or stretches infinitely outward. These geometrical properties are not merely academic. They play a crucial role in cosmological models that predict the universe's ultimate fate, whether it will expand forever, slow down and contract, or reach a steady state. Amid all this speculation and observation, the scientific process remains anchored in rigorous methodology. Telescopes like the James Webb and Hubble continue to scan deeper and more precisely into the sky, looking for faint signals that might provide new data points to test or refine existing theories. They observe not only invisible light but across a range of wavelengths from ultraviolet to infrared, capturing details invisible to the human eye. These instruments have allowed scientists to map galactic formations, track supernova explosions, analyze star formation, and identify chemical signatures in the atmospheres of distant worlds. Each new data set contributes to a larger tapestry of cosmic understanding, one that remains incomplete but ever expanding. Crucially, these observations have also led to the discovery of surprising anomalies. For example, some of the earliest galaxies detected by the James Webb Space Telescope appear to be more massive and mature than current models of galaxy evolution would predict. These galaxies, which formed within the first few 100 million years after the Big Bang, exhibit a complexity that defies expectations, suggesting that star formation and galactic assembly may have occurred much more rapidly than previously thought. This challenges long-standing assumptions about the timeline of cosmic development, and may require revisions to our standard cosmological models. It also prompts deeper inquiries into the forces and conditions present in the early universe, questions that touch on the very physics of matter and energy at their most primordial. Other surprises include the discovery of rogue planets, planetary bodies not bound to any star, drifting through space alone. These objects, difficult to detect and study, further complicate our understanding of planetary formation and dynamics. Were they ejected from their original star systems by gravitational interactions? Or did they form independently in isolation? Their existence reminds us that space is not merely filled with orderly systems but also with wandering anomalies that defy simple categorization. Similarly, discoveries such as fast radio bursts, brief, powerful flashes of radio energy from distant sources, have generated intense scientific interest. Their origins remain mysterious, though theories range from exotic astrophysical events like magnetar flares to speculative ideas involving alien technology. While the latter may stretch credibility, the consistency and repeatability of these phenomena underscore the richness and complexity of cosmic activity.